Okay, so I'm Rocco Chanelli, nice Italian boy from Minneapolis. And this presentation is about horsepower and torque and truck engines. And I found this picture, and this is a test, and no one's responded to what because I didn't tell you what the question was. But I'll just jump to it. What you see here is an American engineering failure. You see that black stripe on the road? Mm-hmm. Those are oil leaks.
Yeah.
Those are a lot of oil leaks.
Yep.
Can you imagine how many drops of oil had to hit that road to make a black stripe 1,000 miles long, or whatever that was? You know, it's crazy.
You gotta run in Detroit.
Yeah. You know, my kid said that.
You see old photographs of Interstate 80 from the 60s and 70s. There's that streak.
Yep.
You don't see it now.
You go to a truck stop,
A little bit, no.
and the parking lot is shiny black.
Yeah.
They didn't have to pave it because there was so much oil on the ground. They just drove over it enough. It was like concrete. So anyway, before I start this, I want to tell you a story. True story. This happened when we were in Kansas City. We went to the board meeting. I'm on the board of directors. And we went to our favorite casino, and we parked on the second level of the parking garage. And I pushed the button to shut the car off and ready to get out, and I realized the motor was still running. And so what do? You know, you push the button once, it starts, you push it again, it stops. Or maybe there's an in-between or something. Anyway, it's modern technology. And I played with it over and over again, trying to get the engine to stop running. Finally, I got out of the car, and here, on the ground level below that ramp, was a generator that was running. And that's what I was hearing. And I told my wife, I said, don't tell anybody. You know what she said? I'm going to tell everybody. It's my favorite.
Yeah, this way too good to keep quiet.
Yeah. So I'm not going to tell any more family secrets. Okay, so anyway, that's that. I wanted a clicker to make that work, but they said I couldn't have that. So, button. Okay, so here's a bicycle. When we're talking about torque, we're talking about how hard you push down on the pedals. We're talking about horsepower, we're talking about how fast you turn the pedals. Okay, and there's one other thing too. In one revolution, there's 2 torque impulses. First the right foot, then the left foot. That's how bicycles work, okay? Any questions? Can't have a question yet. He didn't tell me what to do when I hit the button. Oh, okay. So you've seen this in every physics book. And by the way, this is not a college level thermodynamics course. There was one thing standing in my way of going to college, and that was high school. So anyway, here's some numbers. 1 horsepower, 33,000 pounds, 1 foot in 1 minute. You know, my problem is I couldn't figure out how you make a horse go 1 foot in 1 minute. So the numbers are right, and there's actually 3 things we're talking about here. We're talking about weight, we're talking about distance, and we're talking about time. So we go way back, and I'll tell you, I got another illustration of what James Watt is the guy that had to develop this, the horsepower. And the reason he had to do it is because he was trying to sell steam engines. And if you're selling a steam engine to a guy, he's going to want to know, well, how many horses will this replace? If you can imagine back, this would have been like in 1870, a long time ago. You're going to convert from horses to a steam engine, it was going to be a huge investment in money. And if you are in a cold weather state like Minnesota, you can't just have a steam engine, you got to have a building to put it in, or your water's going to freeze in the wintertime. So anyway, and if you bought one that was too big, you were wasting fuel. And if you bought one that was too small, you weren't going to get your job done. So he needed to have an equivalent figure for you to mark, for him to market steam engine. Some ways it was simple. If you were using a horse to pump water out of your mine, you could measure how many gallons it pumped, and you could use that as an equivalency. If you were hoisting ore out of your mine, that was another way to do it. And if you were hoisting ore out of your mine and it was coal, that was really the deal, because now you got the fuel you need for your engine. And of course, one thing that was good about steam engines was you could burn solid fuel. You could burn wood, you could burn coal. In fact, we've heard stories that when the steamboats were going up and down the Mississippi, they literally deforested both sides of the river, hiring people to cut wood to fuel these steamboats. So anyway, back to my story. Hoisting ore and pumping water was simple, but then he got a customer that was a brewer, and he was using horses to power his refrigeration equipment. So now all of a sudden, there's no easy way to measure how much steam engine you need. And I'm pretty sure that the very earliest steam engines were probably built as they sold them. I don't think there was a big steam engine showroom, and you'd say, well, I'll take that one. Or you could call Sunbelt and say, bring me a steam engine over and we'll try it. So anyway, that's why he needed to formulate what one horse did. Okay, so this is probably easier to understand. Now we got a horse that's walking around in a circle. And he decided, James Watt, that horse could pull 180 pounds. And then he took the diameter of the circle and multiplied that times pi, 3.14, and got a distance. And then he determined that horse could walk around that thing 2.4 times a minute. So now we've got a weight, we've got a distance, and we got a time. Let me see what, come on. This is a more simple explanation. You can see this is a threshing machine. I'm not a farm guy, but that's what they told me it was. Or maybe because it says it there. And I can, because I'm a good mathematician, this is a 3 horsepower threshing machine. And you notice there's a big gear, a bevel gear, because they had to change this walking around into rotary motion with probably a flat belt to power this threshing machine. And they tell me that when you're threshing, you're knocking the grain off the stalk, right? That's what threshing is?
Right.
Somebody else is cutting it. Bundling, yeah. And then later on, they had a machine that would do both, and they call that a combine, right? They combine the cutting and the threshing. This isn't about farming or anything, but most of you guys know if you want to lose a lot of money, just get into trucking. But, okay, so now...
Or farming.
Or farming, yeah. You don't have to own a bar or liquor. Okay, so this diagram here I drew. And you're probably saying, well, I had that figured out right from the start. So there's a horse, 12 foot. The thing that's different about these illustrations is that there's no torque because the horse is moving this around the circle. When we have an engine, then the torque starts at the center. which we'll get to in a second. I was kind of hoping the bottom of that would show. But anyway, 144 trips an hour, which was 2.4 trips a minute, 181 feet a minute, and you multiplied all that together and you got 32,520, and he rounded it up to 33,000. So that's where those numbers came from, 33,000 pounds, 1 foot in 1 minute. And if you use 2 horses, then it was 33,000 pounds, 1 foot in 30 seconds, which makes sense too. If you're trying to get to the top of the hill, the guy with the most horses is going to get there first. Simple as that. Okay, any questions? The next slide's going to be a surprise because I don't remember what it was. Okay, so now we got another number. We need to show you these numbers because engineers love numbers. 6.213, and if you did the math and you divided that by 2, you'd come out with 3.1416. So if we're using foot-pounds torque for a unit of measure, then the lever would be 1 foot long, and you'd put 1 pound of force on it. The diameter of the circle would actually be twice that, because a 1 foot lever going around in a circle, the 1 foot is the radius of the circle, not the diameter. So anyway, you work out that number right there, and you divide the 6.2831 into 33,000, you get this number down here, 5252. So this is a formula where you have to know the RPM and the torque, and from that, you can calculate the horsepower. Because most of us probably know that you use dynamometers for measuring horsepower on engines. But in reality, we don't measure the horsepower. We measure the torque, the twisting force. That's what we're measuring. And then we put it in that formula, and you get the horsepower. And you probably also would realize that if the RPM was 5252, then the torque would equal the horsepower, which doesn't apply to our truck engines because we don't have 5,200 and 52 RPM truck engines, which isn't exactly true. Back when I was a trucker, there was a lot of guys running gas engines, and some of those, I know the 409 Chevys, you could wind them up to 5,000 and run them there all day long. And at the end of 1 year, you'd have 100,000 miles, throw that engine away, and put in a new one. And a brand new complete engine in 1968 was $500. And all the torture that it took to drive those old gassers, what they tell me is that every month they get 1 free trip because the truck weighed 3,000 pounds less than a diesel. So for a long time, they did that. Another thing you had to do if you're running those 409s, they know, is every Sunday before you left, you had to put in new spark plugs. They made it a whole week at one time. And you'd pull them out, and the electrode, the center electrode's gone. Hardly ever see that anymore. You know, there should be a better way to do this. Okay, so this is the formula. You don't have to write this down. Now this doesn't have anything to do with my lecture, but you can see that if the engineers that design trucks, they have a formula for everything. And we don't have to go through what all that stuff is, but they want to turn everything into numbers in order to be able to calculate stuff. Now, just for some of you people that aren't real familiar with four-stroke and two-stroke, we'll just go through this real quick. The part down on the bottom is a crankshaft, and you're looking at it from the end, so you can't really see it. But this was invented by a guy by the name of Nicholas Otto back in 1861. And the question I have is, did he also invent a carburetor? Did he invent spark plugs or ignition system? Because all those things are necessary to make an engine run. But anyway, in the intake stroke, let's start with the compression stroke. You fill the cylinder with fuel and air. And you're going to learn today that filling the cylinder with air is really where horsepower and torque comes from. It's all about getting the air in the cylinder. Gasoline, of course, is a liquid. It's far denser than air, so that's easy. Another thing about gasoline is it's really fussy about the mixture. We know today that it's about 14 parts air to 1 part fuel. So 14 pounds of air to 1 pound of fuel. And when you burn that, by the way, you get 1 gallon of water, and the rest is carbon dioxide. People seem to think that you get carbon monoxide from your exhaust, but that's not true. You get carbon monoxide when you don't have enough oxygen to burn all the fuel molecules. If you've got enough, then you'll have 2 carbon atoms and the oxygen. If you don't, then you only have 1. So that's the difference between monoxide and dioxide. And then, of course, you get that gallon of water. If you live in Minnesota, you can actually see it in the wintertime. Looks like the white stuff coming out of the exhaust pipe, which is really water vapor. Another time you'll see it is if a car or pickup truck starts out in front of you with a cold exhaust system, you'll see a liquid run out of the tailpipe. And that's water. And where that came from is when the exhaust went into the muffler and tailpipe and all of that, it cooled down enough so it became a liquid again. Another fact you maybe don't know, fun fact, is that if you had a blimp, a dirigible, I didn't get any out of it. They saved that water. They had exhaust condensers that would condense the water out of the exhaust, and they stored that on board, because the problem with a blimp is that if you got too light, you couldn't get home. So by keeping the water, they basically kept the same amount of weight. And another thing I learned, because I read about this, the Hindenburg, which was famous for not a very good reason, had 4 16-cylinder diesel engines that powered it. Mercedes-Benz diesels. Not many aircraft used diesels. But anyway, back to this. Compressing the gas, and there's a ratio between the piston at the bottom of the cylinder and at the top. We call that the compression ratio. And the earliest engines had about a 3.5 to 1 to 4.5 to 1 compression ratio. And is that low? It certainly is. Modern engines are in the 11 to 1 ratio. The important part of compressing that gas as tight as you possibly can is you got more energy from it. But, well, when we get to the next slide, I'll show you what happens if you don't have the right fuel. Okay, and then the spark hits. We push this piston down, and this is actually the first time the engine's run after all this other stuff's gone on. Now, it's going to start to rotate. And then the next stroke, piston's going to go back up, push the exhaust gas out. Exhaust valve's going to close, and then we're going to go over here, and the piston's going to go back down. And when it goes back down, it creates a vacuum in the engine, and that atmospheric pressure pushes through the carburetor into the intake manifold and into the engine. And you fill the cylinder with fuel and air. Now, modern engines are what they call direct injected, where they have the fuels introduced right into the engine, same as a diesel. The only difference is you have much lower pressure pushing the gas in. And by doing that, it eliminated a problem with the compression ratio. Okay, so that's a 4-cycle. The crankshaft has to rotate 2 times for one power stroke. This is a 2-cycle, and truckers know about 2 cycles because back in the middle 30s or early 30s, and maybe it was because of Plessy Cummins, that General Motors decided that they would get into the diesel business. And the amazing thing is that what Plessy Cummins did all by himself, General Motors probably had 100 engineers designing an engine. And we think that they decided on a 2-cycle design because locomotive engines at the time that were coming online were 2 cycles. Today, 2 cycles are gone, and I'll explain what happened later on. Although the container ships and the big oil tankers, the biggest ships in the world are still 2-cycle for whatever reason.
Or aren't they opposed, most of them opposed business?
We're going to talk about that, but they're not.
Sorry,
But we will. There was such a thing. I don't think it's the next slide, but so over there where you see a supercharger, technically it's not a supercharger. We think about superchargers in automotive applications to add a lot of pressure, air pressure to the cylinder. But in this case, it only makes the air flow into the cylinder and push the exhaust valve out through the top. And on these engines, Detroit engines, the blower or supercharger ran at twice engine speed. And one of the unique things about Detroit engines is that the block was symmetrical, so you could have the blower on either side. It just depended on which way you put the motor together. The head was the same way. If you wanted the exhaust manifold on one side, you could switch it around. By changing one gear in the back, the gears that ran the camshafts, you could reverse the rotation of the engine. So it was pretty unique, and there's really nothing that's been built since then that was quite like that. A simple application is if, in fact, they used 2 of these engines in a Sherman tank towards the end of the war, and they were sat side by side. So one engine had the blower on one side, one on the other, and then the heads were turned so the exhaust manifolds were in the center. And that was all possible because of the way they engineered this thing. Another thing they did during World War II was they geared 4 of these engines together. It was called a quad, 2 facing forward and 2 facing backwards, and the gearbox was in the middle. And they used it on LSTs, or landing ship tanks. And the reason they did that is because they couldn't build the locomotive engines fast enough to supply these landing ships, because they found that the landing ships was the fastest, simplest way to get a lot of equipment onto the beach. mostly in the Pacific. Because when you go to war, you got to bring everything. Everything, bullets, beans, what's the third thing? Bullets, beans, and something? Because nothing's going to be where you're going to fight. You have to bring it all with you. Okay, so anyway, we'll talk more about this later. Oh, and the other thing that GM did is they had what they call the unit injector. So every part of that injector is all contained in one thing. You just bring 60 pounds of fuel pressure to the injector, and when the rocker arm pushed it down, everything was done. The throttle, because in diesels, again, you have to throttle the fuel. There's no throttle plates in the intake manifold, so you have to do everything with the fuel. Okay, so this is a Model T Ford engine. And I picked this one because there were so many of them. You know, engines come and go, but if you really had a good design, you sold a lot of them. This thing right here is called a crank, and that's how you got the motor started. And nowadays, you ask someone like my daughter, she says, "Dad, the car won't start." And I'll say, "Does it crank?" And she says, "No, it won't start." So the whole meaning of that thing, which was meant to turn the engine over, to start the whole process, nobody knows what that means anymore. And the really old guys know that you never wrapped your thumb around that crank handle, because if it kicked back the other way, it was just about guaranteed to break your thumb or your wrist or your arm. So this was a 22 horsepower engine. It had 79 foot-pounds of torque at 1,500 RPMs. Not much, but the car didn't weigh much either. It had a 2-speed semi-automatic transmission. There's 3 pedals over there. You can't see all 3. Oh, you kind of see them. And actually, there's, one thing about my presentation is that everything I talk about, you could actually go out to the show and find, which makes this whole place kind of unique. But the 3 pedals, one was a reverse pedal, one was the brake pedal, and one was the transmission shift pedal. You push it all the way down for low, and you let it all the way out for high, because that's all it had. It's 2 speeds, but it was only a 35-mile-an-hour car, so how many speeds do you need? And then the whole crankcase, transmission and engine, was all under one crankcase. And remember my first slide that had the oil spilling on the ground? The way you check the oil on this is there were 2 petcocks back here. Does it say? Oh, man, here's. You open the top petcock, if nothing came out on the ground. You open the bottom one, the lower one, and if oil came out of that one, you were good. If nothing came out of that one, then you had to dump some more oil in it. And it never occurred to anybody that, well, we're throwing the oil on the ground here. What's up with that? Another thing this engine didn't have was a water pump. It just used hot water rises, cold water comes in at the bottom. They called it a thermosiphon. Henry Ford was pretty sharp about how he designed this thing. What he wasn't real sharp about is that in 1925, 26, 27, not everybody wanted his car anymore. Not everybody wanted a black car. Henry Ford said, you can have any color you want as long as it's black. But if you wanted a Chevrolet, they came in colors. So little by little, and by 1927, I think this is the right number, Chevrolet outsold Ford. By then, they were ready to introduce the Model A. And the Model A got them back on top again. But that was a little bit behind the times on how that should happen, which just reminds you that sometimes you think you're so right that you're out of business. Although Henry didn't go out of business. And I think as the story goes, Henry's son Edsel wanted to get this Model A Ford to market, and Henry kept saying, no, they're getting what they want. And I think towards the end of production of Model T Fords, they were around $325, which actually started the middle class, because common working person could afford to buy one. Okay, so one of the things that held the horsepower back was bad fuel. Today, the additive we put in fuel to fix that problem was called octane, which was a lead, tetraethyl lead was a chemical. It was highly poisonous. You could get lead poisoning from it. But what it did is it prevented this from happening. The piston is coming up on the compression stroke, the pressure is rising, the spark fires the fuel off, and the way it's supposed to happen, they call it the flame front, is like a field that's on fire, and the fire's burning across the field. That's the way it's supposed to be. But in this case, before all the fuel burns, the remaining part explodes. They call that detonation. And detonation is a bad thing. If you took the spark plug out of that cylinder and it was all covered with aluminum, I'll tell you where the aluminum came from, on the top of the piston. So in order to prevent detonation, you just couldn't have high compression ratios. So all through, even till after World War II, compression ratios rarely made it above 6-to-1. Some of our most powerful engines did it on 6-to-1 compression ratio. But, and detonation can still happen today. Usually the race car guys have to worry about that. You know, there ought to be a better way than walking back here every time. I put this one in here because this particular truck, they called it the Dragon Wagon. It was the biggest truck that anybody had during World War II. It was conceived by two brothers on the West Coast, the Nucky brothers. Chain drive in the back, front axle drove, and it had a Hall-Scott engine. In the early days, you didn't necessarily have to build an engine to sell a car. A lot of companies sold engines because you were used engines for a lot of things besides cars. If you were on the farm, you could have your threshing machine, you could have your baler, you could have your elevator, you could have a whole bunch of farm stuff that I don't know about because I'm not a farmer. But anyway, this had a 1,090 cubic inch 6-cylinder engine made by Hall-Scott. Kind of a unique motor. This went on, and the way they tell me, this was the first 1,000,000-mile truck engine. It would go 1,000,000 miles between overhauls. And they always show a picture of a Kenworth pulling a propane tanker. And this company used these engines, and they got 1,000,000 miles. Well, the thing about that picture is that those engines ran on propane. Because if you were running them on gasoline, they were a good strong 1 mile to the gallon truck, maybe 2 on a downhill. But that's kind of an expensive way to drive. Now, if you're hauling your fuel, you got a better deal on it. So one of the things that made this engine unique for 1940, pushing the button, is it was an overhead cam. So you're looking at the end, up camshaft up there, 2 valves. What did you do with my laser pointer? One innovation was sodium-cooled valves, 2 spark plugs. If this was, and this is kind of a hemispherical combustion chamber, but they couldn't sneak the spark plug into the top. And of course, the thing about an overhead cam engine is that the block is much simpler. You don't have the cam down there. You don't have the push rods going up. You got more head bolts, more room to place the head bolts. You can get the intake and the exhaust ports placed better. There's just a whole bunch of reasons. And strangely enough, this has finally caught on with most of the big diesels today. Most of them are overhead cam. Although we can go back, I think the 1693 Caterpillar was overhead cam, and the 1674, anybody know that, was overhead cam. So, one more picture. Oops. Oh, what happened? What did I just do? Nope. You didn't tell me how to.
You lost it, but then
I hit the. Yay! Figured that out. I didn't have to ask that 6-year-old over there how to bail me out. So this, you had to drive the camshaft, and I would have thought this would have been an all-gear drivetrain, but it wasn't. It actually had a roller chain that drove it. But they still said million-mile engine. Another thing I found out is that International Harvester bought engines from Hall Scott because they couldn't, when they were building Hoover Dam, the first thing they had to do was they had to build these bypass tunnels on each side, 50-foot high tunnel, 50-foot diameter tunnels, so that the river would be bypassing the job site. And all that rock they blasted out of the mountain, they had to haul out of the base of the dam site to the top, get rid of it. And I'm guessing that they also use that as part of the aggregate for the concrete. But International Harvester apparently used, it was 85% of those dump trucks were Internationals. I thought they were Max, but they weren't. So here's a couple fun facts here. A gallon of gasoline, 120,000 BTUs. Diesel fuel, 137,000, which pretty clearly explains why diesels just have more power than gas engines, because there's more energy in the fuel. Another thing is that over there on gasoline, they don't have regular gas and mid-grade and premium gas, because it doesn't matter. The BTUs of heat is the same, whether it's premium or regular. And the difference between premium and regular is that ability to prevent detonation. It slows the burning. So don't ever buy premium gas if your car requires regular. It's senseless to buy premium. And in some cases, it's going to create some issues about getting the thing going in the wintertime in the cold. So keep that in mind. And now, of course, electricity is kind of sneaking in on us. My son is a 2 Tesla family, and of course they're all for it. Let's see. Kerosene, typically jet fuel, and way down here, number 6 diesel fuel is so thick that you have to heat it to get it out of the tank. But most ships burn number 6 because it's cheaper. This was 1939. Dodge converted one of their engines from gas to diesel. It was a 331 cubic inch flathead six-cylinder, and they thought that there was a market for a medium-sized engine. We classify our diesels in three classes: heavy duty, medium duty, and light duty. A heavy duty engine is what we have in all of our over-the-road trucks. They're usually about 2,000 RPM engines, and they weigh between 2,200 and 3,200 pounds. An engine like that really wouldn't work in a medium-sized truck because it would overload the steering axle. So the next classification would be a medium-duty diesel, and we have tons of those way back. The DT 466 for International, probably the all-time greatest engine ever. The 5.9 Cummins, that was close on the tail. The 3208 Caterpillar, those are all 9-liter International V8. Those are all medium-duty engines. They were all around 1,200 pounds. And if you were around back in the 60s, 70s, and you started up a whole fleet of 3208s, within about 10 seconds, you couldn't find your way back to the shop because of the white smoke. That was a big problem with big cubic inch, naturally aspirated engines, is that you got a lot of white smoke when they warmed up. There was so much area that it took a while to heat that all up. So a lot of white smoke. Nowadays, any kind of smoke is bad. In fact, I remember back when I used to service some fire trucks for a fire department, I'd take them out behind the shop and I'd start them up and let them run, warm them up. And pretty soon I'm getting complaints from I was going to say the gals in the office, from the people in the office about the smell from the diesels. And I said, well, what are you going out there for? Well, we're taking our smoke break. Well, okay. The Keystone Museum in wherever they're at, Virginia, they have one of these trucks, the Dodge. So this was the engine. And what Dodge had to do to make this work was just redesign an overhead valve cylinder head. And these are easy to recognize because you can see the injector nozzles are sticking straight into the motor. This was called a Lenova system. And if you're a Mac guy, you know about Lenovas. And you probably know even better than me that they didn't work. In the early days of diesels, there was a lot of experimentation with combustion chamber designs. We know today that direct injection injector at the top, that's the one that made it. This one was a pretty dismal failure. I think I have another. There's two reasons why this engine failed. 95 horsepower, 225 foot-pounds of torque. This was terrible as far as horsepower and torque went. I keep thinking if I move this, I won't have to walk around here every time. Another thing about, this is 1939, for sure World War II wrecked this engine because the whole Allied Army, the Americans, the Canadians, the British, the Russians, were all gasoline powered. But anyway, back in those days, most truck drivers could change a set of spark plugs, they could adjust the points. They could do that. If there was a problem on the side of the road, the driver could pretty much handle it. With this newfangled diesel, they didn't know what the heck to do. Another problem was where you got fuel. They didn't have truck stops back in those days. You know, in the earliest days of gasoline engines, you had to go to the drugstore to get gasoline. Little by little, of course, it was more available, and then, of course, in the cold weather states, you had that problem with your diesel fuel getting thick in the wintertime. So you put all those, and then it was a lot more money, and it wouldn't even run with the gas engine, which was really bad. You know, you think you'd spend all this money to get a diesel, you know, to show all them gas jobs the way home, and it was kind of the opposite, you know. So anyway, this disappeared. I think it was only sold in 1939, and of course after that, everything went to war production, so they weren't going to build it anyway. Oh, ooh. I can't touch that touchpad. Next. Oh, God. Oh. It's called helping the handicapped. So here's 5 different combustion chamber designs that we saw. Top one is the one that's lasted the longest, direct injection. The next one down, if you're a Caterpillar guy, you'd probably remember that was their system with the pre-combustion chamber. Quite a few of their engines use that. A lot of guys call their cat a clatterpillar because they were so noisy when they idled. And that was one of the reasons. This one down here is figure number 10, the ARCO system. International tried that on the DV550, not an award-winning engine. Although eventually, the DV550 started out as a 549 gas engine, and then Harvester made it a diesel. They called it a DV550. But they were just spec'd wrong. They were putting trucks that are way too heavy for the power the engine put out. So eventually, they changed that engine to what they called a 9-liter. If you do the math, it comes out to 550. And they put those in medium-duty trucks, and they were much more successful with that engine. And by the way, 1 liter is 61 cubic inches. So if you just do the math, 7 liter, 427 cubic inches, L10 Cummins, 610. Most everything is in liters today. Next one. So this is a horsepower and torque chart. We're probably going to talk about torque now. You notice that number up there, 606 foot-pounds of torque. About the same torque as a really old diesel pickup. These were naturally aspirated, of course. This was actually the highest horsepower in that series of engines. It started out as the HB 600, and this one grew up to be a 2. Now, you know, I'm lying to you because it says NH up there. NH, the N was for new H. And if I wouldn't have told you that, you wouldn't have known, right? But I'd be up all night pacing thinking I lied to you people. So anyway, the torque was the same, very low. So here's the thing about torque. You're going down the road in your truck, and you're overcoming the wind resistance, the resistance of the tires, the friction in the drivetrain. All of those things are adding up to how much torque it takes for you to go the speed you're choosing to go. And we'll say that 600 would do it. You know, in those days, a lot of trucks ran 220s, 250s, 671 Detroits, which were known as 238s, and they were all kind of in there, and they all ran neck and neck. So That's about how much torque it took to go down the road, not counting a headwind or a hill. So nowadays, the same thing is true, is you're going down the road and it's taking 600 foot-pounds of torque, but you come to a hill, and now the torque demand is going up and up and up, 600, 700, 800. So all you have to do with a modern truck is just step on the gas harder. Or if you got cruise control, road speed governor, cruise control, it just does it for you. You don't have to do anything. You know, just keep talking to mom on the radio or on your phone. But in those days, 55-mile-an-hour trucks were pretty common, and that was about as good as they did. But it was good enough in the day. In fact, I remember I was at a Minnesota Maintenance Council meeting, and they were talking about, I think it was Hyman Freightways was the guy that ran the place, the air shield on the roof of the cab. Minnesota, we called them snowplows, but, and this guy was talking to his friend. He says, you know, all those things do is make the truck go faster. And I thought, you know, you're not getting it quite yet. But the reason he said that is because it was a real common run to go from Minneapolis to Chicago. But you couldn't send one truck from Minneapolis to Chicago because they'd have to spend the night in Chicago. So what they did is they went halfway. The guy from Chicago went to Mauston or Black River Falls, and the guy from Minneapolis or St. Paul met him in Mauston or Black River halfway. And then they'd switch trucks, and then they'd get back. Well, if the trucks went faster, then these guys got back and didn't have anything to do. And you couldn't have that, right? You can't have a truck driver that's getting paid to drive a truck that gets in an hour, half hour early, and he's got nothing to do. So that was a bad thing. Well, eventually they figured out that you could do the same speed and use less fuel. And since then, trucks have become way more aerodynamic than they ever were back then. Although if you think about it, a B model Mack was a pretty slippery truck, like compared to a Cracker Box. You know, like how aerodynamic is a brick going down the road, you know. And the old Macks were really known for better fuel economy than Detroit's or Cummins, even though I would say 70% of all the trucks on the roads are either a 250 Cummins or a 671 Detroit. There was a lot of them. And of course, the Detroit engine was well known. They said the simplest way to drive it is slam your thumb in the door and then drive the truck. If you were mad at it, you couldn't hurt it. Cummins were a little more fussy about who the driver was. But then in those days, they had real truck drivers. Today, we don't know. We know a lot of things about truck drivers. If you ever work at a dock, you know that a lot of the new drivers, new American drivers, can't make them go backwards anymore. They have some struggles with that. But, you know, it's a big jump from herding goats to herding Freightliners. So, that wasn't racist, was it? You probably heard that wrong. So here's three of the most popular, well, I shouldn't say three, two of the most popular Detroits. This is a 6B, but it's the same specs, 238 horsepower. The V8 was a 318. And then the V12 was 434. The 671 and the 318 were pretty much 4 mile to the gallon trucks. That was pretty much what you got. The difference back in the day, I used to haul beer from Minneapolis to Bemidji, 200 miles one way, 400-mile round. And when I'd leave, the boss would give me a $20 bill. And that $20 bill would buy 100 gallons of diesel fuel. And I could make that round. And my wife's in the audience, so I can't tell her about the hot waitress in Sauk Rapids, but I couldn't stop there because their fuel was $21.9. I had to go to the one that was $19.9 because I'd run out of money. And 2 runs down the road, I'd be out of fuel. So down at the bottom, you see some numbers, 1,950 pounds, 23 and then that V12 was 3,300 pounds. It was a really powerful engine at the time. And one of the problems that was happening in Detroit Diesel is that truckers wanted more horsepower, but they didn't really have a way to get more horsepower. They turbocharged the 318, that made it a 350. Eventually what they did is they just came up with the 92 series. 71 is the cubic inches per cylinder. The 92 was bigger, and that solved one problem. That solved the horsepower problem. But then sometimes things misfire when they design a new engine. And they had, the 92s had trouble with the O-rings that sealed between the cylinder head and the top of the block. And if they leaked, you got antifreeze in the pan. And if you had antifreeze in the pan, you could spin the main bearings. And that was a bad thing. Because there was no way you could fix that engine in the chassis, then you had to pull it out. And that hurt a lot of truckers. So usually the way it went is you'd be all about Detroit diesels until you had an expensive problem. Then you switched to Cummins. And then, of course, you found out there were some problems with that, too. So then you switched to Caterpillar. And Caterpillar went through some growing pains, too, with their engines. But eventually, the 3406 turned out to be a really good one for Caterpillar. Until they decided that we're not going to jump on this emissions bandwagon. We'll just stop selling these engines. We use this engine in other equipment we have. We'll just be in the equipment business. And along with the other thing that happens with PACCAR had their own engine. When they bought DAF out in Holland, they had an engine, and so Peterbilt and Kenworth brought that over here, and I think that's a pretty good motor. But with Caterpillar, or with Peterbilt and Kenworth selling their own motor, that really would dig into Caterpillar sales. So they just said, that's our biggest market, PACCAR, we'll just quit. So they did. Today, there's military Caterpillars. The biggest truck they have today, the heavy equipment hauler. We actually saw two of them when we were coming down here to the show. They used to use the 500 horse version of the AV92, and then they got rid of all of that. I guess you just buy all new trucks, right? What the heck's the difference? We're paying for them. It's not like it's their money. And they're using a C18 Caterpillar that's a 700 horsepower version. Because Abrams tank, and that's what they transport, Abrams tanks, weigh 60 tons, 120,000. And they're supposed to be able to transport them across country, so big horsepower. Next one. So here's some numbers. I found all of this down at headquarters in Kansas City. These are 90s Cummins engines. And the funny part about all truck engines is that they always rate them by horsepower, even though it's the torque that gets you down the road. But these are some pretty common ones. Of course, the 350 was really a big seller for them. And if you had a 350, then you wanted a 400. The 400s were way better. You can see a couple 100 pounds of torque extra. One thing we learned in Minnesota is that for some reason, the 350s would start at like 0 degrees. A 400, you could never get started that cold. They just,
Less compression.
yeah, they probably had more manifold pressure in the 400, so that made them harder to start. But in my time as a mechanic, one of the things that happened in the 70s, early 70s, was we switched from 30 weight engine oil to 1540, and that was a big deal.
Oh, yeah.
Getting trucks started. And then the Group 31 battery with the studs on it, that was a big deal. And then when they came out with the gear reduction starters, we got those first with the Thermo Kings. We used to have trouble because there wasn't any easy way to plug those things in to warm them up. Well, what we would do is we'd take a vice grip and we'd clip it on the glow plug toggle switch, and that would hold the glow plugs on, and then we'd go have coffee. And when we came back, them babies would start right up. But then they came out with that gear reduction starter, and between the 1540 and the batteries in that starter, we hardly ever had trouble with them getting them things going. Okay, and again, this whole series of engines were like 2,400 pound engines, which is important for a lot of different truckers. Like if you're hauling gasoline, not many backhauls from a gas station.
Next one.
Yeah.
I've got to go, so I'll move this one.
All right, if I get,
No, hang on to everything. I'm leaving that camera. Take your time.
no, there's a clock right there. Oh, it's already 2:30?
Yep.
Oh, okay.
You can keep going.
All right, I'll have to, because I haven't got done yet. That's why everybody's leaving. So this is a triple. You see there's 3 trailers back there. And this is what I know about cab over Freightliners. If the windshield wipers are down here, that's newer than the ones where the windshield wipers are right under the windshield. But anyway, what you're seeing there is that plume of black smoke, and it's not that long. So what we see there is that guy just grabbed another gear. He just upshifted, and he stood on the gas, and until the turbocharger spun up, so we had more manifold pressure, more air to burn the fuel, you got that big shot of black smoke out the stack. If it smoked like that all the time, you wouldn't be able to read PIE on the side of the trailers. It would be all black. And of course, that was a single axle. That must have been a trick to drive that thing on an icy road. Man. Okay, so let me tell you a thing or two about Detroit diesels. Because in the 90s, General Motors Allison division came out with a brand new engine, a 4-cycle 6-cylinder, the 60 series. In one fell swoop, all the 2 cycles went away. So here's the deal with the 2-cycle. Let me see if I can find it. Is this a different picture of the same thing? Hopefully this one more. Oh, okay. This is a little out of sequence. This is your 2 opposed piston engine. This is a Fairbanks Morse. Crankshaft at the bottom, crankshaft at the top, no valves. The pistons would come together on the compression stroke fire. When they went to the opposite end, one end was the exhaust, the other end was the inlet, and of course there was a supercharger to push the exhaust out and fill it with air. Fairbanks, this was just a huge engine, 8 1/8 bore, weighed about 13,000 pounds. Submarines had 4 of these in it. And a friend of mine served in the Navy, and he said his job, when they had to pull the pistons out of one of these engines, the first thing he had to do was take the crankshaft off, the top crankshaft off. And his job was to count cotter keys. Every nut that held that crankshaft in had a castellated nut with a cotter key. And of course, you didn't want to drop a cotter key into the motor. So that was his job. He had a string of wire, and he'd slide these cotter keys on it to make sure it didn't drop anything. But you lift the crankshaft off, then you can pull, and then down below you could access the connecting rod, disconnect that from the lower crankshaft, and then you could pick out the whole thing. It's never a truck engine. Come on. I'm holding you over time now, so if you're waiting for me to, I'm trying to make that arrow go over to that arrow. Goodness. I had a couple of pretty cool pictures. Well, anyway, let me just finish this off so you can get going. The thing with a two-cycle that they could never change was a short power stroke. With a two-cycle engine, once that piston got down and uncovered the intake ports, that was it. That's all the pushing that piston could do after that, because the next thing that had to happen is the ports were uncovered, the exhaust valves opened up, the pressure in the air box pushed the exhaust out and brought in fresh air for the next stroke. The crankshaft swung around, the piston came up, covered up the ports, and then you had the compression stroke, which was shorter also, and then you had the power stroke. It worked great with naturally aspirated engines. Remember, Cummins 250s and 671s ran together. But later on, that 250 Cummins got to be a 600 Cummins, and the Detroit just stalled at their horsepower. I'd like to show you a couple more slides if I can make this thing work.
I saw the guy putting it on the line. I don't know if that's.
Oh, over here?
Yeah. There you go.
Okay. So what you see here, this is a four-cycle from top dead center down to where you see the exhaust valve opens. That was the power stroke on the two-cycle engine. Got it. One more. Oh, I missed that slide. You can see that at 90 degrees after top dead center, that Detroit engine was over. The power stroke had to end right there because then you were uncovering the ports. And that was just an intrinsic design of two-cycle engines. You couldn't change that. Okay, so, hello? You see the shape of the ports. If there's any Detroit diesel guys in here, if you see those ports through that handhole, that engine is a virgin. That one has never been overhauled because that's the very earliest port configuration, way back in 1936. They just drilled a bunch of holes in there. Later on, the big D-shaped port is what we see today. There was an intermediate one they called the figure 8, which was two smaller holes with the center out of it. And that shape they call the figure 8. But every time you overhauled an engine, you put in new liners, you always put in the latest and greatest liners. So if you ever see that, those are kind of collector's items for here's an engine here. You can get an idea how big this is because there's people working on it. This is a 567 locomotive engine, which was also a two-cycle. You see the two guys working on top. They're putting in the cylinder liner, the connecting rod, the piston, and the cylinder head is all one thing. And that just dropped into the motor, and there was four big, they called them crab nuts, that held that whole assembly into the block. There was no cooling water in the block. The water jacket is part of that liner, and that was all connected together with manifolding. So those, and I don't know if this engine is, it could be, it's all fabricated steel, it's not a casting. It's just steel plates welded together, and that Fairbanks Morris engine was the same way. I think I got one more. slide. I got a slide that not many people have ever seen. Oh, jeez. Maybe it knows that this presentation is over. Got it. Well, I guess it's over. What, the next slide, if I could get it up here, was a 16-cylinder, two-cycle Detroit diesel engine. They called it the Pancake. It's not going to work. Oh, this thing right here. This is 6 hours from here. Is the okay? So that's how far I got there. What you saw in that picture was a winch drum that held 9,000 feet of cable. It's at the Quincy Mine in Hancock, Michigan, 6 hours from here, straight north. And that's how far it was to the bottom of the mine. And that drum was that size, so the cable would never overlap. It would hold the whole 9,000 feet in one wrap on that thing. So not only is that the biggest mine hoist in the world, it also has the biggest steam engine in the world to run it. And that engine is so big, you can't take a picture of it. And you're thinking, well, why can't I take a picture of it? Well, because it's inside a building, you can't back up far enough to get the whole thing. It might be, I don't know if anybody's going north when they leave here, but that's a really interesting place to go. Hancock, Michigan. Quincy Mine. If you're going to Googleize it, that's what you do. Quincy Mine. Okay, any questions? 10 cents a piece. Well, thanks for coming, listening to my blah, blah, blah. Hope you learned something besides.
When you were saying about the, where you had to get fuel,
Yeah.
you had to pass the one with the nice waitress to go to the cheaper. Well, I ran out of fuel one time trying to get to that waitress.
That's our secret.
Have you kept up with Volvo lately? And some of the engineering and advertising that they're, with their engines nowadays, they're not talking horsepower.
Aren't they?
They've eliminated horsepower out of any of their brochures, any of their, they're talking torque only.
You know, another thing I saw was clutch engagement torque. That's a new kind of a buzzword. Because of these automated manual transmissions, it's important that you have high torque at 600 RPMs because you don't have a person letting the clutch out anymore. You got some kind of a hocus pocus stepper motor thing that gets the truck rolling. You know, it might be one of the hardest things for a driver to learn, for a potential driver, is how to get the thing rolling, you know.